and welcome back. Today we're going to be talking about the exceptions to the octet rule. This is more drawing, which I'm sure you guys are going to be really excited about. There are three types of compounds that will have less than 8 electrons around one of the atoms. We classify these three types as less than an octet, free radicals, and the expanded octet. This expanded octet I'm going to make a separate video on because it's a rather large section that we're going to talk about. It involves a lot of different atoms. So the first thing we're going to look at is less than an octet. When we talk about compounds that have less than 8 electrons, essentially what we're talking about are boron compounds. Boron's been shown to be stable when it only has 6 electrons around itself. And we're going to do an example here with boron trihydride. If you remember naming boron, we only have 1, and then 3 hydrogens, trihydride. So we're going to go through this like we did with any other drawing. We're going to start by counting up electrons. Boron has 3 valence electrons. Each hydrogen has 1 valence electron, and we end up with 6. Well, looking at this, we know that hydrogen can only make 1 bond, so it cannot go in the middle. So we're going to put boron in the middle. Boron goes right in the middle, and now we're going to create our bonds to each of the hydrogens. 1, 2, 3. We've used 6 electrons, so we don't have any more left. And this is the compound we've come up with, or this is a drawing we've gotten to. This is actually the stable form for boron. And so we don't have to worry about anything else. It has less than 8 electrons, but it is stable. Here, moving on to free radicals, this is really exciting. These were discovered at the University of Michigan, point of pride. But radicals have an odd number of electrons. This is a very strange thing because normally we've been working with everything that has even number of electrons. That makes a nice, that's how we get an octet, and we have 2 electrons in each bond, or 4 or 6, depending if we have double or triple bonds, plus the lone pair. So we've always been working with even numbers of electrons. Free radicals have odd numbers of electrons. They're rare and they're highly reactive, so they don't stick around for very long. So this one, we're going to talk about nitrogen monoxide. It's on, if you look at it backwards. And so we're going to count up the electrons. We have 5 here plus 6, we get 11. All right? These are not things that I'm going to be asking you a lot of questions about, but just so you know if you ever run into them, how to draw them. First, we're going to draw the Lewis dot structure for nitrogen and oxygen. So nitrogen looks like this, and oxygen looks like this. And when we see free radicals, we want to make sure at least one atom adheres to the octet rule. And you can see here that oxygen is able to make 2 bonds because it's got the 2 lone electrons, whereas nitrogen is able to make 3. So in this particular case, the element with the odd number of electrons is going to be nitrogen, and here's the reason. If we look at these 2 single electrons here, they can link up and form a single bond, and then these 2 electrons here are going to link up, which gives us our double bond. Once we do that, we have this single electron on nitrogen, and the octet rule is fulfilled for oxygen. And we're going to get to formal charge in a little bit, but this stabilizes the compound slightly because if you think about it, nitrogen is supposed to have 5 valence electrons. In the way that we've drawn it here, we have 1, 2, 3, and then nitrogen has put 2 electrons into the double bond, so it's like it has 5 valence electrons still. Oxygen has 1, 2, 3, 4, and it has also put 2 electrons in the double bond, so it's like oxygen has 6 electrons. So these are 2 of our exceptions to the octet rule. In the next video, we're going to look at the expanded octet.